Let's show the full mechanism and the ultimate product with these reagents. I want to show the mechanisms and the product. So far, so good.
And then we would have a resonance form with the pi bond on the other oxygen.
That's a good point. That's a good thing to notice in the back of your head. We don't need to draw that resonance structure, but it's good that you notice that.
Now, if I remember, when you have a Grignard's, it's going to go, you're going to probably get another nucleophilic attack, or not?
Let's talk about that. I think you worked this out well, but let's talk about this. Let's see. So you turned the Grignard into an ionic compound, and you did that without adding or dropping carbons, so that's good. Then you showed this as a nucleophilic attack on this carbon. Now, why is it reasonable for this carbon to act like an electrophile? There's two reasons why it's reasonable for this carbon to act like an electrophile.
Because it has its electron density being pulled from both the oxygens on either side of it.
Yes.
Making it a delta positive.
It's got a delta positive. That's one good reason.
And then it also has a resonance form that makes it a positive.
Good. It's really good that you're looking to use resonance. In fact, if we think more, there's two resonance structures. There's one resonance structure where this pi bond moves over here, and there's another resonance structure where this pi bond moves over here. So there's also resonance structures where this carbon has a full positive charge. So it's totally reasonable for this to act like an electrophile. I think you saw this reaction in that previous video series, and it's good that you remembered that. But even if you had never seen this reaction before, we should still be able to figure out what's going to happen here based on our previous principles. You got all the charges right. You didn't add or drop any carbons here, so that's good. It's always important not to add or drop carbons. This isn't very important, but if you wanted to, you could show the magnesium bromide as the counter ion over here. That's not really very important. Then you showed that the second set of reagents was protonating us. That was good too. Why do we have to wait till a separate step before we add the acid and the water?
Because protons are going to ruin a Grignard.
Good, good. We have to keep Grignards away from acids, and we even have to keep Grignards away from protic solvents like water. Even just water would be enough to protonate this Grignard and ruin it.
So you wouldn't get a second attack of a nucleophile at that point. Once it's reached the acid, then it would basically render it ineffective. You wouldn't have a second attack.
That's good. That's a really good analysis. That's exactly right. So the Grignard here has attacked once. Now, can a Grignard attack this compound again is this compound right here with the negative charge electrophilic? No, the negative charge eliminates the electrophilicity. Things with negative charges are not electrophiles. So the Grignard can't attack this because the negative charge here is making this non-electrophilic. And by the time the negative charge is gone, the reason it's gone is because we've added this hydrochloric in the water. Well, that's completely destroyed any Grignard we had left anyway. So that's the analysis that you gave. So it was good that you asked whether the Grignard could attack twice, and now you figured out why it can't. The Grignard can't attack this a second time because the negative charge means it's no longer electrophilic. And by the time it loses the negative charge, we wouldn't really have any Grignards around anymore because they've been destroyed by our water and our acid. Good. So this really is the final product. We should just stop right here. That's sometimes the hardest part in this term, knowing when to stop, but this is the place to stop. You worked all that out. That's very good. What type of functional group is this?
Carboxylic acid.
Right. So we should take stock of where we are. What did we start with today? Well, we spent a long time on the acid-base chemistry of carboxylic acids. Because carboxylic acids are stronger acids than any other organic compound we've seen, one of the main ways that this will be tested is acid-base chemistry. So we spent maybe almost an hour just on the acid-base aspects of that, including how we can use that for extraction. But now we've moved on from there. Now what we're talking about is how to make carboxylic acid. So this is one of the most important ways to make a carboxylic acid. As you saw from that previous series, this is called carbonation. The carbonation reaction, which I guess means adding the carbon dioxide here. You've probably heard of carbonated soft drinks, right? A carbonated soft drink is one to which carbon dioxide has been added. Well, this is a different type of carbonation. We're carbonating the Grignard by adding carbon dioxide, and it turns out that gives us a carboxylic acid.
And this is one of the main ways that carboxylic acids are made?
Yeah, I would say it's one of the main ways. In that other video series, I think you saw two other ways, which, what were the other ways?
Lithium cuprate? No.
That was something you can, yeah. So the other ways were nitrile hydrolysis and oxidation. Now, nitrile hydrolysis is not covered in your lecture notes here, so maybe that's not something your instructor is focusing on too much. And I don't even, the other way was oxidation, which actually I don't see, that's a little weird. Your instructor didn't really seem to cover that much either. So actually, it seems like your instructor is really only covering one way to make carboxylic acids, which is carbonation. So those other parts of that last video might not have been too important for you, actually, now that we look at it.
They still reinforce the basic principles of it.
Actually, now that I see it, your instructor had one other way of making acetic acid. Right, that's a little less important. Maybe we'll come back to that if we have time. So yeah, the main way your instructor is focusing on is carbonation. Oh, and it looks like you're already comfortable with that, so that's good. One important thing to notice here is, when would you use this on a synthesis problem? Well, you would use it if you have to make a carboxylic acid, obviously. But notice you would use this to make a carboxylic acid with one additional carbon. Notice how we started with 5 carbon molecule, and now we have a 6 carbon molecule. And that's always going to be the case because when you add the carbon dioxide, you get the 1 extra carbon. So that's one thing to keep in mind. This is a way of making a carboxylic acid with 1 extra carbon.